Hello, everyone. A warm welcome from the Australian National University, and I hope that you and your loved ones are keeping safe and healthy wherever you are. My name is Jay, and I look after international relations and partnerships here at the ANU in the areas of sciences, health, and medicine. I'm joined today by my colleague Arthur Shu, and of course, we're very lucky to have with us our distinguished Professor Chenupati Jagadish. Before we start, I would like to acknowledge the Nanowire and Ngambri people, who are the traditional owners of the land where ANU is located and where we are broadcasting to you today from. And I pay my respects to their elders, past and present. Now I'm very quickly going to try and introduce our speaker for today, Professor Chenupati Jagadish. Professor Jagadish is a distinguished professor and head of Semiconductor, optoelectronics and nanotechnology group in the Research School of Physics here at the Australian National University. He also holds honorary positions at many institutions globally, including at University of Oxford, University of Cambridge, Chinese Academy of Science, University of Tokyo, and many more. His research interests are based on neuroscience, neurotechnology, compound semiconductor optoelectronics, nanotechnology, photovoltaics, and materials science. His research activities and achievements are actually too many for me to cover in this short introduction, but just to give you a quick indication, he has published more than 950 research papers. Over 680 of those are in leading journals. He holds 5 US patents. He has co-authored a book, co-edited 15 books, edited 12 conference proceedings, and 18 special issues of journals. Professor Jagadish is also currently serving as past president of IEEE Photonics Society and is the editor-in-chief of Applied Physics Review, editor of 3 books, and serves on editorial boards of 19 other journals. For his achievement in research, he has been elected as a fellow of 11 science and engineering academies and 14 professional societies. They include the Australian Academy of Science, the US National Academy of Engineering, the US National Academy of Inventors, the American Physical Society, an honorary fellow of the Indian Academy of Sciences, and many more. Professor Jagadish has also received many national and international awards. Again, I'll only be able to list a few of them here, such as the IEEE Pioneer Award in Nanotechnology, IEEE Photonics Society Engineering Achievement Award, IUMRS SOMIA Award, a UNESCO Medal for contributions to the development of nanoscience and nanotechnologies, the Lyell Medal from the Australian Academy of Science for his contribution to physics, and the list goes on. Professor Jagadish has also received Australia's highest civilian honour, that is the Companion of the Order of Australia, for his contributions to physics and engineering, in particular to nanotechnology. Professor Jagadish and his wife Vidya created the Chenupati and Vidya Jagadish Endowment at the ANU to support students and early career researchers from developing countries to visit ANU for up to 3 months and carry out a research project. Inspired from that, the ANU College of Science created the Future Research Talent Program, which also provides funding to students from selected group of high-quality partner institutes to visit the ANU. Together, the Jagadish Endowment and the Future Research Talent Awards now support over 100 students to visit ANU to carry out their research projects. I think I'll stop here and hand over to Professor Jagadish so he can tell us more about semiconductor nanostructures for optoelectronics applications. Over to you, Professor Jagadish.
Thank you very much, Jay, and good afternoon to all of you, those who are participating in various parts of the world. And then it's really a pleasure and honor for me to speak to all of you. And as Jay mentioned, my name is Jagadish, and I'm from the Australian National University. And so in addition to optoelectronics, and I will also be covering some aspects of energy and neuroscience as well. And during this talk, and as also been mentioned, I have honorary appointments in various parts of the world. And it's really a pleasure to be associated with so many of my colleagues in various parts of the world. The beauty of science is that there are no national boundaries. We can all work together. So for the good of the society and also really doing exciting science. So before I proceed further, I would like to acknowledge my collaborators in various parts of the world. And then really, today's talk is a collective effort between my group at the Australian National University and many groups in Australia, US, UK, China, and Sweden, Italy, Russia, Switzerland. Again, because of the fact that there are no national boundaries, we can all work together. And it's really been a pleasure for me to be working with my colleagues in various parts of the world. And in particular, I would like to thank all the postdocs and students, those who have contributed to the research in these groups. I've only listed the academics in those groups, but really many students and postdocs have contributed to it. Without their passion and hard work, there's nothing much to talk about. So I want to thank all of them. This is my group at the Australian National University, And typically we got 10 to 12 nationalities at any one time. It's a really bright young people, and it's really a pleasure for me to work with all of them. And I want to again thank them for all their contributions to our research, and their passion and their dedication and commitment is the one which leads to exciting science and wonderful results. I also take this opportunity to thank our funding agencies for providing us a little bit of funding, which is allowing us to have fun. And that's really important. I do science for fun, and then in fact, and if they're not giving money, then we'll not be able to have fun, which is not good for us. So here's an overview of my talk, and I'll give you the motivation why we're interested in semiconductor nanostructures. And then I'll talk about how do we grow these nanowires and nanostructures, and then talk about nanowire lasers and LEDs, terahertz detectors, nanowire solar cells, the use of nanowires for photoelectrochemical water splitting, and also nanowires for neuron growth. And we also work on terahertz modulators, but I'll not have time to really cover that topic as well. Before I proceed further, I would like to thank all the groups, those who are working in various parts of the world in the area of semiconductor nanowires and nanostructures, and for their contribution to the research, because science is really built on the knowledge generated by various groups, and then really we learn from each other. So that's why it is important for us to acknowledge other groups, those are contributing to our science. So before I proceed and then talk about nanostructures and nanowires of semiconductors, let me just talk about technological revolutions which have transformed the world and the society. We all know that the first technological revolution started with the steam power and leading to mechanization, and second industrial revolution started with electrical power, started with the mass production. And third industrial revolution started with computer power and automation. And people are predicting the fourth industrial revolution will be really bringing the digital world and then the biological world together, and then really leads to interfacing of the machines and humans. And light plays an important role because about 80 to 90% of the information which we receive is through light. So really, light-based technologies are going to really play an important role in terms of bringing the machines and humans together. And currently, light-based technologies are about $1 trillion Australian dollars of industry. And then people are predicting by 2030, and these industries will be doubling also because of the fact that the light-based technologies are playing a very important role. So the World Economic Forum in 2018 have identified some of the key technologies which are needed for the next generation industries and the society. And they've identified holographic displays, wearable optical sensors, and light navigation and communication like LiDAR, for example, for autonomous vehicles or so. And then also 3D vision and gesture recognition, and then enhanced machine vision and augmented reality. But all these aspirational technologies require fundamentally new approaches for smart and miniaturized optical systems. And then we are really developing and working toward developing these technologies through our Australian Research Council funded the Center of Excellence on Transformative Meta-Optical Systems, involving multiple research groups and about 5 research groups in the country, and then which I will come back and then talk to you. In the Center of Excellence, and then what we're doing is that we are really covering the generation of light using nanostructures and manipulation of light using nanostructures and detection of light. So really developing a metamaterials where you're able to really generate light and manipulate the amplitude and the phase and then the polarization of the light, and also be able to detect that one, and then which could potentially lead to some things like flat lenses and a wide variety of technologies. This particular center is led by my colleague, Professor Dragomir Neshev, and then about 5 universities, including ANU, in fact, ANU is a host institution for this center. And then it's really an exciting time for us with about 15 CIs from 5 universities in Australia, about 20 partner investigators from various parts of the world as well, including Oxford, Cambridge, Caltech, and other places. So let me now come to optoelectronics. What is optoelectronics? So we all know about electronics, and we also know that about silicon is the workhorse for the microelectronics industry. And then today I'm able to talk to you because of the fact that I've got a computer here, and then of course all of you are also using through your computers or smart devices. And most of these devices are made out of silicon because silicon is a workhorse for the electronics industry. But unfortunately, silicon is not a good light emitter because it's an indirect band gap semiconductors. I cannot make LEDs based on using silicon, for example. You need to have something called a direct band gap semiconductors, where the minimum in the conduction band and the maximum in the valence band is happening at the same wave vector. So those direct band gap semiconductors made out of the 3,5 semiconductors of the group 3 of the periodic table and group 5 of the periodic table of gallium arsenide, indium phosphide, gallium nitride, indium nitride, and all these combinations of these elements of these materials. So really, optoelectronics is conversion of light into electricity, for example, using solar cells and photodetectors, or conversion of electricity into light using light-emitting diodes and lasers, for example. So for example, development of the nitride-based semiconductors has led to the development of the blue LED, which was missing because earlier we had a green and red LEDs based on the other semiconductors, but the blue was missing, but the development of the nitride semiconductors led to all the 3 primary colors, leading to development of the white LEDs and the LED light bulbs and things like that sort of thing. And in fact, 3 of the Japanese scientists, those who developed the nitride technology, has won the Nobel Prize in Physics in 2014. The same materials which are used for making LEDs can also be used for making lasers. And in fact, the development of these LEDs has led to the solid state lighting and also the large area displays, which are in fact, this is the one which is shown in the Times Square in New York in the daytime. You're able to see the TV and the large screens because of this high brightness of these LEDs, for example. And also that we use the same materials for making infrared detectors, which are used for biomedical imaging applications or night vision applications, and even in manufacturing, where to see where the heat is generated in a computer chip, for example, and while you're operating the computer chip, so that you'll be able to really distribute the transistors so that you can really redistribute the heat. Heat generation is a major issue, for example. The same semiconductors are also used for making solar cells. For example, nowadays, you can get efficiencies of the solar cells as high as 47%. And, but of course, these semiconductors, solar cells are very, very expensive. And in fact, these are developed for space applications where satellites are expensive and you want to really keep the satellites going for a long time. And then these multi-junction and compound semiconductor-based solar cells are used for that purpose. But now people are also exploring how they can be used for terrestrial applications by using concentrator systems. So because of the system cost is so high, they want to have the most efficient solar cell in this focal point of this particular concentrator here. Today, I'm able to talk to you because of the fact that we got this internet through the optical fiber communications. So the electrical signals from my computer have been translated into an optical signal using lasers, and they are modulated and then sent to the optical fibers. And then you are converting these light signals into electrical signals using photodetectors. And these are all operating in the 1.3, 1.55 micron window region of the optical fibers, because that is where the lowest absorption and the dispersion takes place. So now let me move towards nanowires or nanostructures. So people are predicting that the nanowires are considered as the building blocks for the next generation electronics and photonics. And say, for example, if we can make these nanowires of the different materials with the different lattice constants on different substrates without the constraints of lattice mismatch. But when you're making the two-dimensional thin films or so, you always have to worry about what is the lattice constant. Lattice constant to the unit cell of the crystal, which repeats itself. And so then whenever you get the large lattice mismatch, they dislocate and they lead to defect formation, which makes it useless for the making optoelectronic devices. But whereas these nanowires, because of these nanoscale and also three-dimensional architecture, either they expand or contract depending on the differences in the lattice constant between the substrate and the semiconductor. You can also make axial heterostructures. For example, this green material is different than the red material. So that means you can put quantum disks and quantum dots within the nanowire. You can dope these nanowires in P-type and N-type so that you can make PN junctions. Because if you want to make an LED or a laser or a solar cell or a photodetector, you need to have the PN junctions. And by doping different parts of this nanowire with the different types of dopants, like in the case of gallium arsenide, for example, zinc and silicon, and we're able to make them as a PN junction. So that means we can make a single nanowire-based LEDs and lasers or so, which I will come back to. You can also create radial heterostructures. This pink material is different than the red material. So you can really create a core shell nanowires, and these are so-called radial heterostructures. Also, you can create the branch nanowires, which again opens up three-dimensional architectures in these cases. So here are some examples we made in our own laboratory where we have shown the gallium antimonide nanowires can be grown on top of gallium arsenide nanowires. Despite large lattice mismatch, we were able to show that you can get atomically perfect nanowires of gallium antimonide on top of gallium arsenide. You can also make the branch nanowires of indium arsenide on top of gallium arsenide. They could be used for cantilevers and or the scanning probes and the range of applications. Also, we can create nano trees, which are very good for energy harvesting applications like a generation of hydrogen by splitting water, for example. You can also start moving from the nanowires into nanomembranes, and that's where when I talked about nanostructures, and I'll be talking about these nanomembranes. Most importantly, International Technology Roadmap for Semiconductors, and these are the people, those who are really determining what technologies are needed for the electronics. They've identified nanowires are also a key technology component for the next generation electronics. And in fact, IBM Zurich now recently have demonstrated indium gallium arsenide high-speed transistors on silicon by bringing the 3-5 semiconductors and silicon together. So thereby they'll be in the future, we'll be able to bring both optoelectronics or photonics and electronics together on the same chip. So if the nanowires are so much of interest and importance, and how do we make these ones? So there are two main techniques which we use. One is called as a metal catalyzed VLS growth process, which I'll come back to, or the other technique is called selective area epitaxy. And we use a technique called metal organic chemical vapor deposition, or MOCVD. And there's also an alternative technique called molecular beam epitaxy. And you can choose whichever the technique which is accessible to you in order to be able to make these nanowires. In the case of metal catalyzed VLS growth process, we introduce some nanoparticles of gold on top of a semiconductor like gallium arsenide, for example, typically about 50 nanometer gold nanoparticles, for example. Gold had gets a melting temperature of more than 1000 degrees Celsius. But once the gold reacts with the gallium or aluminum or indium, and then you create the gold gallium eutectic liquid, and which got a melting temperature as small as 350 degrees Celsius, the alloy. Gold gallium, gold aluminum, and gold indium alloy temperatures much, much smaller. So now if I introduce this gallium arsenide wafer with the indium gold nanoparticles into the MOCVD reactor, heat it up to somewhere between 370 to 500 degrees Celsius, and then introduce the gases needed for the growth of gallium arsenide, for example, trimethyl gallium and arsine, they get incorporated, it gets supersaturated, crystals start precipitating out. You can see the beautiful nanowires which are grown by my former student, who now a professor at Cambridge University, Dr. Hannah Joyce, where she has demonstrated demonstrated the excellent atomically perfect nanowires. And sorry for that. And we were able to show that you can get beautiful cylindrically shaped nanowires which are also atomically perfect nanowires. You can also create ordered patterns of the nanowires using selective area epitaxy. In this case, we don't really use any metal nanoparticles, and we deposit some silicon dioxide by plasma enhanced chemical vapor deposition, put some photoresist, and do electron mimeography, create patterns of holes. You transfer those patterns through silicon dioxide so that you can expose indium phosphide, and then put this one into the MOCVD reactor, heat it to somewhere between 650 to 750 degrees Celsius, and introduce the gases needed for the growth of indium phosphide, the trimethyl, indium, and phosphine. And then these gases dissociate, and you can create these beautiful indium phosphide nanowires, which are ordered patterns of these ones because we created ordered patterns of holes here. This is the work of Dr. Qian Gao, and who is now a research engineer in Blue Glass in Sydney. We've gone off and looked at the light emission from these indium phosphide nanowires, and by excite these nanowires with a laser pulse and look at the light coming out of these ones. And then we quantified the quantum efficiency of the light emission from these nanowires, and then compared these ones with the epitaxial layers or the two-dimensional layers which we grow, and then they both show very comparable quantum efficiencies, indicating that they really show an excellent performance despite large surface area of these indium phosphide nanowires. So we've gone off and then asked ourselves, instead of opening a hole in this mask, what will happen if you open a slot or a ring? And then we'll be able to really grow what type of interesting structures we can grow. This is the work of my student, Dr. Nayan Wong. And then he has spent about 4 years, again, taking indium phosphide substrate, put some silicon dioxide mask, put some photoresist, do electron beam lithography, either create a hole or a slot or a ring, and then try to grow these nanostructures and then see what type of structures we can get. So again, he spent a lot of time in optimizing various growth parameters. And again, when I'm showing you various slides, a student or a postdoc might have spent 2 years or 3 years sometimes to get these good quality results. And I want to thank all of them there for their hard work. So here is a case where when Nayan Wong opens a slot along a particular crystallographic orientation of this particular crystallographic orientation and puts into the MOCVD reactor and then heat it up and then introduce the gases needed for the growth of indium phosphide, you can see you can create these beautiful membranes with these 5 side facets with this particular crystallographic orientation. But if you open the slot along another crystallographic orientation of this particular 1112 bar, and again you grow these nice membranes, but these membranes are thicker than these ones, and then the facet which you are creating is different than this one because of the crystallographic orientation differences between this slot and this slot. But if you open this slot in between these two, so then what happens is that you create these beautiful diamond-like structures with these alternating facets of these particular facets and this particular facets, for example. So now you can see, instead of just making nanowires, we can make nanomembranes and nanodiamonds and a wide variety of structures, and for a wide variety of applications like MEMS applications and a range of nanomembrane lasers and others. So what will happen instead of opening a slot, open a ring. And again, you can see that you can get a beautiful ring-like structures. And then if you really keep on growing, they really fill this one up, and then you end up ultimately finishing off with the beautiful hexagonal membranes here. And then these membranes are very useful for a wide variety of optoelectronics applications. And in fact, most recently, my new student, Wei Wong, has demonstrated a ring resonator laser. And in fact, this paper just has been published today, accepted in Nano Letters or so, which is really exciting to be able to develop a wide variety of lasers, for example. So in fact, we've gone off and looked at the light emission from these structures, and then using cathodoluminescence, instead of using laser pulse, and we use electron beam here, excite the electron hole pairs, and we look at the light coming out of these ones. You can see there's a very uniform light emission coming from these particular structures or so, indicating that Nayan Wong's hard work of 4 years has really led to excellent performance from these structures. And Nayan Wong is just starting as a postdoc fellow in ANU at the moment. So now let me move from materials to devices. So as you know that the lasers, and all of us have studied undergraduate optics courses, you need to have a laser cavity, you need to have a gain medium, and then you need to pump the gain medium to create population inversion. And as and when the model gain is equivalent to the optical losses, lasing starts taking place. These are undergraduate optics courses all of us have studied. These mirrors really bounce the light back and forth. And once the gain is larger than the losses, lasing starts taking place. In fact, here's the equation for the threshold condition for lasing. What essentially it says is the gain need to be equal to the internal optical losses and then the mirror losses which are taking place, then only the lasing starts taking place. So we take one of these nanowires, and then if you shine light from the top, light starts coming from the both ends of the nanowire, because nanowire acts like a waveguide, and then the light gets reflected from the both ends of the nanowire because there's a large refractive index difference between 3.4 of the nanowire and then the surrounding medium of 1. So now you can see I don't really need to put any mirrors or anything of that sort. If I design my nanowires carefully, every nanowire should act like a laser. So that's what we are really trying to do, and trying to design and then be able to make these wide variety of lasers, for example. So we've in fact, during the last a decade or so, we've demonstrated a wide variety of lasers, and I'll not have time to go into the details of all of them. Dr. Drew Saxena has demonstrated gallium arsenide nanowire lasers, who is at Imperial College now. And then Dr. Qian Gao has demonstrated indium phosphide nanowire lasers, who is at Blue Glass. And then Dr. Tim Burgess has demonstrated zinc-doped gallium arsenide nanowire lasers, and then who is at IP Australia now. So now let me give you one or two examples. So first we design these nanowire cavities so that we really be able to identify what should be the height and length of the nanowire, what should be the diameter of the nanowire or so. And then this is a work of Drew Saxena, where he has looked at the various optical modes which are propagated into these nanowires in a 260 nanometer gallium arsenide nanowire. And he is demonstrating this particular optical mode, which has got the highest intensity at the center of the nanowire, for example. So he plots a threshold gain for lasing as a function of the diameter of the nanowire for a nanowire of about 10 microns long. You can see that the smallest threshold gain for lasing is for the nanowires, which are about 250 to 300 nanometers. And in fact, if you really use a smaller diameter nanowires, threshold gain for lasing is so high, before they start lasing, you start creating a lot of damage in these nanowires. So, excuse me. And he plotted the peak gain as a function of the carrier density. And also you can see the nice threshold-like behavior. And then above certain carrier density, the lasing starts taking place. And threshold carrier density is also dependent on the temperature of the device as well. So to cut the long story short, and then based on Bruce's design and Dr. Jenny Jiang and Nain Jiang, who is now at Cambridge University as a postdoctoral fellow, she has grown these gallium arsenide nanowires and then transferred them onto a glass slide. And Drew Saxena has done the measurements. And where you can see that the below threshold, you see a very broad light emission like a light emitting diode. Above threshold, you see a sharp light emission like a laser. And because it's acting like a fabric cavity. You can also see beautiful interference fringes showing that there's a coherent light is coming out of this one. In fact, Drew Saxena has done simulations, and simulations and experimentally measured coherent fringes really match very well. And then you can also see the output power versus pump intensity, and then you can see the threshold-like behavior or so. And then the log-log plot showing that this is S-type behavior, confirming that these are really lasing. These are the first gallium arsenide nanowire lasers operating at room temperature. We reported about 8 years back. And then also these are some of the smallest lasers you can think of. And just to give an idea, and I can put about 20 lasers on the width of your hair. That really tells you how small they are. Smaller the laser, they consume less energy. Smaller laser, you can switch them on and off faster. That means they can be used for faster communications or sensing and a wide variety of applications. So in fact, we started using these nanowire lasers for a wide variety of applications. And in fact, this is work which is jointly with the University of Strathclyde, Professor Martin Dawson's group. And they developed a technique called nanoscale transfer printing, where they come up with a PDMS stamp and pick up the nanowire, and then they can drop it off wherever you want, precise nanoscale location of these nanowires. So here's an example of the case where they have really transferred these ones onto a glass slide and a flexible glass slide, so that they could be used for flexible optoelectronics applications. And then you can start seeing the light coming from both ends of the nanowire. Also, as you can see the threshold-like behavior and a narrow line width showing that even after transferring, and all these nanowires are lasing, indicating that this transfer process is a gentle process, for example. So then I asked them that, can you be able to put these nanowires in front of the waveguides so that you can couple the light into a waveguide? There's a Y-junction waveguide for multiplexing and demultiplexing applications where you can couple these ones with an optical fiber, for example. Here, they're able to successfully be able to put these two nanowire lasers here and then be able to demonstrate that the light is coming from the other end of the nanowire, indicating that really it's this really very useful for making for a wide variety of applications. And again, this work is work of Dr. Dimitar Jevtiks, and then who is during his PhD produced this work. So then I asked them, can you be able to locate these nanowire lasers into nano antennas? So here's the key. This is a work of Professor Fang Ren from Nanjing University. And she, while she was at the ANU, she was designing these so-called terahertz metamaterials. And then these materials she's been designing, and there was he's got something called the bullseye antenna. And then essentially what you got is a metallic antenna here. There was a gap in the middle. And then we requested my colleagues at Strathclyde to be able to locate these nanowire lasers in this gap here. So now you can see that when you don't have this nano antenna, light is coming from the both ends of the nanowire because it acts like a fabricated cavity. But once if this nano antenna is there, suddenly light is coming from the vertical direction. And then again, you can see the nice threshold-like behavior, narrow light emission, and then showing that for the first time, we're able to show vertical emitting nanowire lasers. And they are very useful for things like facial recognition applications and meta-optics applications and holographic display applications and a wide variety of applications. So if you want to couple the light to a waveguide, we can use these particular nanowire lasers. And whenever you want to have the light to be coming out of the surface of the structure, and then you'll be able to use these vertical emitting nanowire lasers. And again, this led to a lot of excitement within the community, for example. So till now, I've only shown you optically pumped nanowire lasers, but ultimately industry wants to have electrically pumped nanowire lasers. And so really, in fact, this is the work of Dr. In-Suk Yang, and he's from Samsung, and then he came and then again returned back to Samsung, where he's a research engineer. So you can see that he spent about a lot of time in trying to make PN junctions. I told you that you need to have a PN junction to make a laser or LED, electrically injected ones. So he doped this indium phosphide with the zinc to make P-type indium phosphide. He has grown an indium gallium arsenide quantum well, and then made the N-type indium phosphide on the top, and then tried to really transfer them to a glass slide and made some electrical contacts using electron magnetography, using titanium gold also on both ends. You can see the actual picture here, or to see the schematic here. So now if you inject current and then look at the voltage drop or the apply voltage or measure the current, you can see the IV characteristics of this particular PN junction diode, showing that diode-like behavior, indicating that he has been successful in terms of being able to make a PN junction and also be able to make good ohmic contacts in structures. So now he injects the current and look at the light coming out of these ones. So you can see that as and when you're increasing the amount of current through this LED, this particular device, and you end up getting brighter and brighter light. And but also you see two emission peaks, mainly because the quantum well which is sitting on the top of the nanowire has got a different thickness and composition with respect to the quantum well which is on the side of the nanowire, which has got a different thickness and composition. And again, these are behaving like light emitting diodes, not like lasers, because there's no narrowing of the line width here, for example, which you would expect for a laser. So, but the good news is that they're emitting in the 1.3, 1.55, the micron window region, which is important for optical fiber communications. But we are not able to get lasing. And we asked the question why. But it turns out, whenever you put metals on the nanowires, these metals have got a large optical losses. If you create a large loss in the cavity, you have to pump them harder to get over the losses. And then if you're pumping harder, you generate a lot of heat, and which reduces the gain of the gain medium, gain peak, and in the process it becomes like a vicious circle. So now my student Nikita Grani from IIT Kharagpur, and then she is now working here, and then she is now working on replacing these nano metals with some indium tin oxide and zinc oxide and other materials. Still you're able to make the connections and then still be able to inject current, but don't have the metals. So that's why our hope is that we'll be able to reduce the losses in the cavity. It's been a really challenging project. Nikita has been working for more than 4 years now, and still it's been very challenging. And then hopefully, and by the end of this year also, we're able to demonstrate electrically pumped nanowire lasers, because those are the ones which are in interest for the people, those are working in industry, for example, and also real world applications. So before In-Suk Yang finishing his PhD and returning back to Korea, he's also demonstrated a nanowire array LED. For example, these nanowires are grown vertically. You fill these nanowires with a polymer material and selectively etches those ones and put some indium tin oxide and some metal on the top and the bottom. And again, you inject the current and or apply the voltage and measure the current or IV characteristics. And again, here more and more current is injected and more light is coming out of these ones. You can see, in fact, the bright light coming at this below the probe here, indicating that he has been successful in terms of being able to make quantum well nanowire LEDs. So, but it turns out that because you're embedding these nanowires into a polymer material, you can peel these things off, and then they could be used as a flexible displays, because Samsung and Apple and others want to use flexible or affordable phones or flexible computers and flexible TV displays and other things. And these flexible nanowire LEDs could be very useful from that point of view. So that's why In-Suk has focused more on making LEDs rather than really pushing too much into the nanowire lasers, for example. So now let me move from LEDs and lasers to terahertz radiation. So terahertz radiation is something which some of you might have heard, some of you may have not heard. We all know about electronics, where we talk about microwaves and radio frequencies and millimeter waves. And then we also know about all the things about the optics, for example. You talk about ultraviolet light and visible light and infrared light. There was a gap called the terahertz gap, where the technologies were limited. Only during the last 20, 25 years or so, people have been developing terahertz technologies, including ourselves, making terahertz lasers and terahertz sources and detectors and other things. So why people are interested in terahertz radiation? But it turns out that the many chemical molecules have got signatures in the terahertz parts of the electromagnetic spectrum. So you can see the lactose and monohydrate and hydrate and other things. Also, a lot of explosives have got also signatures in the terahertz parts of the spectrum. And also many metals are reflected by, the terahertz radiation is reflected by metals. But nowadays, for example, in the airports, they don't use any X-rays because X-rays are ionizing radiation. They create damage to the DNA. But terahertz radiation is a non-ionizing radiation, so that means it doesn't create any damage to your DNA. And whenever you go through an airport and you see a box where you go through, and that's where the people do this so-called terahertz imaging, where they'll be able to detect whether you got any metal particles, metal parts on your body or not, for example. Also, these terahertz radiation could be used for looking at the biomedical imaging, for example, looking at the cavities in the teeth, also wireless communications, and water content in leaves, so that you'll only be watering the crops when they need to be watered, thereby preserving the precious resource like water by using terahertz imaging of these particular structures, for example. Just to remind you, 1 terahertz is about 300 microns in wavelength. So really the far infrared region of the electromagnetic spectrum. So this is a joint work with my colleagues at Oxford University, Professor Michael Johnston and Professor Laura Hertz. And also this is the work of my student, Dr. Kun Pang. Now she's a postdoc at Oxford University. So we've been trying to develop these terahertz detectors. So what Kun Pang has done is that she tried to transfer this nanowire onto a quartz substrate, because quartz is transferred to terahertz radiation, and makes electrical contacts using electron magnetography. And then she shines the light on this nanowire to generate photocarriers, electron hole pairs, and then come with the terahertz pulse. The electric field of the terahertz pulse separates the carriers, and what you measure is the photocurrent as a function of time. As you can see, they are talking about picosecond times. That means it's a terahertz part of the electromagnetic spectrum. And if you measure the current as a function of time, and you can measure the electric field of the terahertz pulse and conductivity of the material as well. So that really helps be able to really extract the full electric field of the terahertz pulse by using this particular technique. So Kun Pang has fabricated all the devices at the ANU, has gone to Oxford University and did the measurements. And then we were able to demonstrate a wide variety of gallium arsenide-based nanowire terahertz detectors and indium phosphide-based nanowire terahertz detectors or so. But again, to cut the long story short, and let me share with you most current results, and where last year we demonstrated a polarization resolved terahertz detector. Instead of using a single nanowire detector, but she tried to really fabricate during her postdoc at Oxford these nanowires, which are really in an orthogonal direction to 90 degrees to each other, to connect to these metallic bow tie antennas, for example. After growing the structures at the ANU, we sent them to Oxford. She fabricated jointly with Oxford and ANU, and then the Strathclyde University. You can see the close-up of this electron microscope image of these nanowires, and then these metal bow tie antennas, and then the nanowires at the bottom. The key challenge has been the top nanowire should not be in physical contact with the bottom nanowires. So that's been a challenge. So that's where Kun Pang has spent a lot of time in optimizing these things. And then what she does is that she takes this, makes these terahertz metamaterials. You shine the terahertz pulse through this one. Terahertz pulse passes through this terahertz metamaterial. It interacts with this material, and the polarization of the terahertz pulse changes. She measures using the X and Y polarization using our terahertz detector. So here is the electron microscope image of these terahertz detectors, with these terahertz metamaterials she has designed. And then our simulations show terahertz transmission should be like this for the X polarization, and the Y polarization terahertz transmission should be like this. And then using our detector, she's able to show that really the simulations and experiments match very well. And for the first time, we're able to make use of these terahertz room temperature operating terahertz detectors, which can measure the amplitude, phase, and then the polarization state of the material. So that's why we're able to publish this work last year in Science. And again, a lot of hard work has been put by Kun Pang and Dimitars and other students involved in this particular work. Again, this work has been jointly with Oxford University and Strathclyde University. So now let me move towards other devices like solar cells. As all of us know that you need to have a PN junction in order to be able to make this a typical solar cell, and you need to make it thick enough to absorb all the light. And then of course, carriers need to migrate long distance for a thin film solar cell, for example. But it turns out that if you use a nanowire, you can make the nanowire as long as you want, and then you can make a PN junction like a core cell or a radial PN junction. So thereby you can absorb the light, all that light vertically, and collect the carriers in the lateral direction. So that means you're able to decouple light absorption pathways and carrier collection pathways using nanowires for the first time. Also, they've got very low reflection losses, so that means you don't need to put any anti-reflection coatings. Also, these nanowires act like light funnels, so that also acts like a light concentrators, which also makes it very attractive. Again, we have really done a lot of simulations of looking at what should be the height of the nanowire, what should be the diameter of the nanowire, what should be the distance between the nanowire or the pitch between the nanowires. You can see that the most of the current is generated at the tip of the nanowire, indicating that we don't need to make a long nanowires. About 1 or 2 micron long nanowires are more than sufficient. Again, simulations show that you need to have a diameter of the nanowires to be around 150 to 160 nanometers, and the diameter to pitch ratio need to be somewhere between 0.5 to 0.6 or so. Again, the simulations play an important role as a guide to be able to make the fabrication of the devices. So here is the nanowires which have grown based on those designs. And then again, how to make contacts is to really fill the gap between the nanowires with a polymer material. You selectively etch that one using plasma etching and make some indium tenoxide contacts at the top and the metal contact at the bottom. And then you shine the light and measure the IV characteristics of these particular solar cells. So to cut the long story short again here, and then this is in fact some of the best nanowire solar cells have been demonstrated by my colleagues at Technical University of Eindhoven and then FOM Institute in Emol, and then where they demonstrated 17.8% solar cells or so, which looks extremely promising because the amount of material which we are using is very, very small, for example. In fact, we started doing is that replacing this polymer material with the organic semiconductors jointly with Professor Laura Hertz at Oxford University, so that you can make use of the best of the both worlds of the organic and inorganic semiconductors, because organic semiconductors have got a good hole mobility, but they got very poor electron mobility. But the 3-phase semiconductors have got a good electron or hole mobility as well. So that means by using this combination, and then we'll be able to make the flexible organic and organic solar cells. We're able to peel these things off very easily so that they could be made use of this as a flexible solar cells. There we'll be able to help you with putting on a backpack your solar cells so that you're able to charge your smartphones and other electronic devices, for example. That's our future goal. So now let me move to another topic of the water splitting to generate hydrogen. As you know that the greenhouse gas emissions has been a major challenge, and then people are looking at alternative ways of generation of energy using hydrogen, because hydrogen is a transportable energy source and also storable energy source. That's why people are interested in hydrogen, and people are talking about hydrogen economy, for example. Say, for example, if you take water and then put some electrodes of a cathode and a photoanode, and then the cathode could be a metal like platinum, for example, and then the photoanode could be a semiconductor, for example, here. If you shine light on top of this semiconductor, you create electron hole pairs, and then the holes will come and then really be oxidizing water, and then the electrons will go there and reducing the protons to be able to generate hydrogen here, for example. So then essentially a clean energy source, and then using water, splitting it into hydrogen and oxygen, using hydrogen as an energy source. And again, this work is driven by my colleagues, Dr. Shiva Karaturi and Professor Holtan, for example. So in fact, we've been looking at what are the best materials for this application. In fact, I borrowed this slide from my colleague, Professor Zetian Mi from Michigan University. His group has did a lot of simulations and looked at what materials are very good. And one of the important requirements is that the redox potentials of water need to be within the band gap of the semiconductor. Here's a conduction band, here's a valence band edge, and then you need to have this thing to be saddling in these two here. So here's a case where you can see that gallium nitride has got is able to do that one, but the problem is that gallium nitride is a large band gap material, but it only be absorbing the UV light. If you do the indium nitride, It's only straddling one of them, but not both of them here. So that means it can only be able to, also it only absorbs infrared light. But if you make indium gallium nitride, combination of indium and nitrogen, and then what happens is that you got a band gap which can absorb the visible light, also straddle the redox presence somewhat. So in that direction, we have been looking at a gallium nitride nanorods, and this is the work of my colleagues from engineering and also from my group in physics. And then you're able to show that we made this ready, my student made bare gallium nitride nanowires by using plasma etching from the top down, and then try to look at the photocurrent density as a function of the over potential. And he is able to show that by coating this cobalt oxide with gallium nitride, we're able to get a very stable performance. But still gallium nitride, as I mentioned, is not the best material. And we're exploring materials like indium phosphide and other semiconductors as well. So in fact, most recently, by using silicon and then perovskite solar cells, we're able to demonstrate a 17% efficient standalone solar water splitting system. And if you shine light and the electricity generated by the photovoltaics, the perovskite solar cell is powering the electrochemical cell, and we're able to demonstrate very efficient things. And in fact, the Cool Earth Forum recently they announced that this is one of the top 10 innovations in 2020. And particularly, I want to thank Dr. Shiva Karturi and my colleagues there. Let me finish off with the last topic of the neuroscience, brain repair. And as all of you know that this is a work led by my young colleague, Dr. Vinny Gautam, who used to be in my group. Now she's a lecturer in biomedical engineering in University of Melbourne. So all of us have got 80 billion neurons, and then they form into neuronal network. And so really, typically that allows us to be able to function. So what will happen if you got a brain damage, for example, due to dementia or other things, or otherwise due to accident or something? So what happens is that you're breaking these neuronal connections. So that means you lose some of the functions, whether you cannot move or talk or do something or the other. We asked ourselves, can we really create a neuronal patch and then be able to make these connections back so that we can be able to provide the functions back to people with various neurological disorders, for example. And in fact, Vinny has spent about 3 years in optimizing these things. And then we tried to use this indium phosphide nanowires and then tried to grow these neuronal cells on top of this one. You can see the cell body of this neuronal cell here. And then these axons really like to follow these patterns of these indium phosphide nanowires very nicely here. You can see the close-up of some of the dendrites which are coming of these axon structures as well. So instead of using a single neuronal cell, what will happen if you put multiple neuronal cells? So you can see that if you do that one, and then this this dotted boxes is the way the indium phosphide nanowires are. You can see the many neuronal cells here, and then these axons really follow these square patterns here beautifully here. But whereas the flat indium phosphide outside this region here, neurons are growing, but they're all making random connections. So that means there is some sort of neuronal engineering is taking place by using these nanowire arrays also here. So what Vinny does is she does something called calcium imaging. She puts a calcium dye. As and when the neurons are firing axial potentials, calcium ions are passing through these ion channels, and then the concentrations of the calcium ions will determine the intensity of the light coming out of this fluorescence intensity here. She takes a video of this one and try to correlate if this neuron is firing, what's happening to this neuron and these astrocytes and wide variety of structures which you got. And she compares this one with the neurons which are grown on nanowires, also neurons which are grown on plain glass substrates which are typically used by neuroscientists, so that we can really be able to compare these two. It turns out that when you grow these neurons on the glass substrates, these neurons are all firing randomly. You can see the change in the fluorescent intensity as a function of time. And if one neuron is firing here and the other neuron is at a different time and other things. So you see very little correlation between these signals which are taking place here. But whereas the neurons which are grown on indium phosphide substrates, they're all firing at the same time and indicating that there's an excellent correlation is taking place. There is some sort of a synchronized and correlated activity is taking place. When Vinny Gautam presented this work at a neuroscience conference about 3 years back, they're all quite excited about it. And so in the process, they were asking Vinny the question, what type of neurons which are growing? Then she said that she is using rat neurons. Then they said, why are you wasting your time with rat neurons? How about using stem cells from the humans so that we can be able to look at the differences between the neurons firing behavior for the people with the dementia, for example, or Alzheimer's disease and other neurological disorders, and then the healthy people, and to be able to better understand and be able to help people. So this project, in fact, has been funded by the Dementia Australia Research Foundation and Neil Gilbert Foundation. And we are now working with my colleagues at University of Melbourne. And then people, those are the stem cell biologists, and then University of Wollongong, they're neurobiologists, and then computer scientists. And so basically applying the artificial intelligence techniques to be able to better understand and how the neuronal signals are taking place from the stem cells taken from the Alzheimer's patients and healthy people, and creating mini brains or organoids without microglia, measuring the microelectrode analysis, electrical signals, and calcium imaging. And again, we are developing the neuroelectrodes so that we'll be able to really measure the signals from the single neurons or so. It's a really an exciting project and really a multidisciplinary project. I'm enjoying working with my colleagues in various parts of the country, for example, including University of California, San Diego, Professor Shadi Daye's group there. With that, let me now conclude. Nanowires and nanostructures open up opportunities for manipulation of light matter interaction at nanoscale and developing a new class of lasers and LEDs, terahertz detectors, and integration of optoelectronic devices on various platforms, and developing solar cells and splitting of water to generate hydrogen, and engineering the growth of neuronal networks here, for example. Okay. So really, I haven't had time to talk about terahertz modulators, mainly due to the time limitations. Let me finish off with some information. As Jay Puria has mentioned, that I'm serving as editor-in-chief of the Applied Physics Reviews, which has got an impact factor of 17.05. And so really, it's looking for high impact original research or reviews. And if you got any breakthrough results also, please submit your work to Applied Physics Reviews. As I mentioned to you about our Center of Excellence of TMOS, and we just filled the PhD positions and postdocs, and maybe keep an eye on this website. We regularly advertise the positions for postdocs and PhD students. And if you're looking for anything, please get in touch with us. And again, Jay Puria has mentioned about our endowment, which is to help the students and young scientists from the developing countries to come and spend some time at the ANU, including our Future Research Talents program, and initiated with India and also Indonesia and other countries as well. With that, I want to thank you sincerely, and I'm very happy to answer any questions you may have.
Great, thank you very much, Professor Jagdish. That was very informative and interesting talk. I hope everyone found it that way as well. We already have some questions that have come in. I don't know if you can see the Q&A.
Yeah, I can see the first question, Bijoy's Jacob. And in fact, Bijoy's turned out that came and spent some time at the ANU as part of this, either the Jagdish Endowment one or FRT scholar, I can't remember, most likely Jagdish Endowment scholar. Jagdish, yeah. And so really, Bijoy's, and mainly we have used materials like BCB and PDMS are the standard polymer materials which we are using for planarization purposes of these nanowire LEDs. And most recently, also we are using SU8. And SU8 seems to be much more easier to selectively etch than PDMS and other materials. And depending on what applications we have, we end up using different polymer materials. And then at the moment, the focus has been with SU8, for example. So the next question is from Deepak Dabur. And so out of VLS and epitaxy, which one is better to make nanowires regarding to the quality and cost? Oh, that's a very good question, Deepak. And so really it depends on what applications you have. For example, the quality of the nanowires is not really need to be, we have demonstrated that you can get a good quality nanowires either with VLS or selective epitaxy, and both techniques could be used. But so for example, if you do not have an access to things like electron beam lithography and other things, by just using metal nanoparticles which have got a low eutectic temperature with one of the elements of the semiconductor, you'll be able to make easily the nanowires, for example. But if you really want to have ordered patterns of the nanowires and other things, but then we are going for epitaxy particularly more importantly, the doping becomes much more easier with selective epitaxy than VLS growth process. In fact, when we try to dope this with the VLS growth process of zinc doping of gallium arsenide, Tim Burgess during his PhD, he has shown that you can get this something called a twinning superlattices. Crystal structures start changing when you start putting into the doping into these VLS structures. So that's where we started focusing more on the selective epitaxy in the recent times. And we do use both the techniques even now, depending on what the purpose of the growth of the nanowires will determine that particular one, which technique we want to make use of. Yeah, if you have any further questions, I'm happy to answer. But if you are feeling shy to ask me questions, and you can also send me an email. And so my email address is c.jagadish@ieee.org, or otherwise Google my name and you'll be able to find my name. Please feel free to send me an email, and I'm happy to answer any questions you may have.
Great, thank you, Jagadish. I think we're on time. Maybe we'll give everyone a minute. If you have questions, if you want to put through now, please do them. Otherwise, you can of course write to Jagadish. And thanks for putting up the link to the ARC Center there, Jagadish. I understand that there may be sometime in the next year or so some more PhD scholarships available through that.
Yeah, thank you. But this is something we regularly advertise. And for example, we just filled the postdoctoral positions in our group and also PhD students. But every year or 2 years, we are always regularly advertising positions. So my advice is that please keep an eye on this website. And so then whenever you see an advertisement, but also remember that it's not just at ANU. These positions are also advertised at other universities as well. By really keeping an eye on this one, you'll get to know where the opportunities are for PhD students and postdocs in all the 5 universities, for example.
Thank you, Jagadish. So there's one more question for you from Jinal.
Okay. So Jinal, can you please, the question is, can you please throw some light if we can make a PIN kind of nanowire using epitaxial growth? Absolutely. And in fact, that's what we are focusing on, Janal. So really, that's a question which is that's where you need to really be able to control the dopants and a P-type doping, N-type doping precisely. But the challenge which we are finding is that how do you measure dopants in these semiconductor nanowires? Because these are very, very tiny structures. I cannot use SIMS like secondary ion mass spectrometry or otherwise Hall effect measurements and all these things. And we've been developing techniques like, the optical techniques to be able to really determine what type of doping concentrations we're able to get. Precise controlling of the doping has been a challenging task. And that's where it took a lot of time for us to be able to make these electrical injected LEDs and lasers and all things. So, but certainly we are making good progress in this area. That's very important, if you want to make electrical injected lasers, for example.
Great, thank you, Jagadish. I can take the second question from Bulus. Yes, we will. Basically, what we will do is we will provide recording of this talk, and you can, of course, see all the slides that Jagadish has gone through in that recording. So we'll email everyone a copy of that recording once it is put up on our website. And so again, on behalf of everyone here, thank you for attending this talk, and thank you for those questions. We do have a few more guest lectures coming through for the rest of this month and in July as well. Tomorrow we have Professor David Nisbet, again talking about nanomaterials and sort of taking down scale devices and talking about their application in health in particular. I understand you work with David as well, Jagadish. So
yes.
If you're interested in nanomaterials, please do come tomorrow. If you haven't registered, please do so. Otherwise, we'll see you soon.